Okay. So, uh, so last time, we discussed that every linear function can be represented by a matrix. And today, we're gonna do. You're slightly behind the schedule, but okay. But mm, so I guess I will need to speed up a little bit. Uh, uh, you know the matrix, and as you know well, every vector has its length, and same is true for matrices. So in this definition, so they're gonna define the length of the matrix, the norm of the matrix. What does it mean? So it is well, so Cij is entry of, well, as you know well, Cij is entry of the matrix C. And this is what? This is, well, they are trying to square every single entry of the matrix C and take a summation and take a square root. Okay? All right, so same as before. Yeah, it's just like exactly same thing that we did when we were trying to find the length of the vector. Okay. And this is the length of the matrix. And for the length of matrix, we have something very similar to the quotient-Schwarz inequality, so which goes like this. Well, C is an n by n matrix, and X is a vector, n-dimensional vector. So, well, in this case, so we're going to consider this X to be the n by 1 column vector. So this is what? So this is a just n-dimensional column vector, right? So, well, therefore, for the left-hand side of this inequality, this is about the length of the n-dimensional matrix. And it is going to say that this length of this n-dimensional matrix is bounded by this is the matrix norm of the matrix, right? Matrix C, times the vector norm of the vector X. So this is bounded by the matrix norm times vector norm, right? Okay, so what is the proof? Okay, so first, we try to compute the C times X. So C times X is C is an n by n matrix and times with times n by 1 column vector. So, well, at least dimension-wise, the matrices involved in this computation looks like this. Well, this is C1, and this is C2. Well, this is C M, and this is matrix X. So this is, well, so what does it mean? So yeah, I draw this horizontal line just to emphasize, so all these rows as a row vector. So these are row vectors. So these are the first row of the matrix 1 and matrix C, second row of the matrix C, and the last row of the matrix X, C, times the column vector x. And, well, and multiplying C by x, so the resulting matrix would be m by 1 matrix, and every entry of this resulting matrix will look like this. So C1 dot product with x and C2 dot product with x, Cm dot product with x, right? I mean, these numbers, because, well, this times that, and this times that, this times that, and summation altogether is going to be, which is precisely the dot product, right? Okay, so, well, therefore, the length of this vector is nothing but the length of this vector. So therefore, we are supposed to square each of these entries and take a summation, and lastly, we take a square root. Then you're going to get this one, okay? So, yeah, Cx is C1 x plus C2 x. Oh, sorry. I should square everything. And Cm x squared and everything taken square root. Okay, good. Now this is time to use the quotient-Schwarz inequality. Do you remember? The quotient-Schwarz inequality says that absolute value of the dot product of two vectors is bounded by the length of the first vector and the length of the second vector, right? So, and since we are squaring everything, so this guy is bounded by length of C1 squared times length of x squared. And this guy is also bounded by length of C2 times length of x squared. And finally, this is also bounded by Cm squared and x squared. So, summarizing, I have a C1 squared plus C2 squared and Cm squared and everything taken square root times vector, the length of the vector x. Okay, good. And this is what? Well, C1 square is nothing but the square of every entry of this first row vector, C1. And C2 square is the sum of square of every entry of the row vector C2. So C1 square plus C2 square Cm square, this is going to be, well, square of every single entry of this matrix C, right? And you take a square root, and this is what? This is precisely the matrix norm of the matrix C. So this is C times X. So we are done. Okay, great. Okay, so since we are talking about functions, and today we are going to study, I want to focus on some more special kinds of functions. There are actually special kind of functions. The function, well, in general, so we should be able to deal with any general function from Rn to Rm, but there are something special, such as Rn to R. So that is, it was sometimes we call the real valued functions. So what are these? From Rn to R. We say they are the real valued functions because their domain is real numbers. such as uh, x times y and x, y, z, and h, x, y is square root of x squared plus y squared. So these are typical examples of the real values functions. So this is, well, this is from R2 to R, and this R3 to R, right? Oh, okay. What is the best way to understand the function? So when you're a high school student, then the best way to best way to understand any real value function is to draw the graph, right? So if you can draw the graph, then you're kind of you're kind of understood the functions. So in our case, we are still trying to draw the graph of these real valued functions. But drawing the graph of real valued function is usually impossible. Why? Because, we are the entities, you're human beings embedded in the 3 dimensions. Therefore, in order to draw the graph, then we are supposed to draw the dimension of domain and dimension of codomain at the same time. So that means the dimension of the domain and dimension of codomain cannot exceed the sum of the dimension of domain and codomain cannot exceed 3. So therefore, all the functions that we can draw, all real value functions that we can draw the graph is a function from R2 to R. Okay. So visualizing functions. The first way to visualize functions is to draw the graph. So from now on, if I say the graph of function, then you should better understand it as a graph of function from R2 to R. So if f is a function from 2 dimensions to 1 dimensions, then its graph is typically looks like this: x, y, z. So graph is the subset in 3 dimensions. XY coordinate is in D, and Z coordinate is in Z coordinate is f of xy. Okay. So, for the purpose of this course, you should be able to imagine the graph of some basic functions, such as what do you think is the graph of this guy? Have you ever tried to draw? Yeah, I know you have the graphing calculator. But without the help, without using the graph calculator, can you imagine the graph of this guy? If you have never tried it before, then this should be somehow complicated. But say that this is x-axis and this is y-axis, and along the x or y-axis, the function, so z coordinate should be 0, right? Because along x and y-axis, then along x-axis, along y-axis, then x and y coordinate equals to 0. But if I go to the somehow diagonal direction between x and y-axis, just like that, the function value should go up. Therefore, the graph should also go up. And if I go this or that direction, then function go up. Either one of the x or y coordinate becomes here. Signs of x and y coordinate are they're different, so they should go down, right? So basically, okay. So yeah, this is class. Yeah, I can use the graphing calculator. Well, Z is XY. Yeah. So I have such a very nice and beautiful picture. So it looks like a saddle. 말한장처럼 생겼죠. 그렇죠? 그러니까 이쪽으로 하면 올라가고 이쪽으로. Usually the graph of a function from R2 to R usually represent some sort of graph embedded in R2. Right? Sorry, some sort of surface, two-dimensional surface embedded in R3. Okay. Great. Okay, this is the one way to visualize your function. But we can do actually even more than this. There is another way to visualize your functions. That is a level set. Suppose that I have a function from Rn to R, which is a real value function, and set up all point and just imagine set up all point from domain of the function that whose function value equals to C. Collection of all such point from your domain is going to be called as a level set, a C level set of your function. Okay. The idea of level set, yeah. So if you have never heard about the level set, then this might sound something mysterious, but actually it isn't. Well, in our real life, in our everyday life, you at least have encountered this notion of level set at least one time. What is this? Like a contour set. 등고성 같은 거 있죠. 그렇죠? 아니면은 일계보 같은 거 볼 때 등합선 같은 거. 그런 게 전부 다 레벨 셋. 그러니까 압력이나 고도 같은 것도 지도를 우리가 R2라고 보면은 지도의 각 포인트에 그 포인트의 고도라는 거기 실수를 어사인한 함수를 이제 R2에서 R로 가는 함수라고 본다면은 고도라는 값이 똑같은 지점들을 연결해 놓은 것을 우리가 등고선이라고 부를 수가 있겠죠. Okay, so this is a level set. Well, the idea of level set does not give the full comprehensive picture as the graph of functions, but level set is a little bit more flexible. I mean, so you can draw the level set from R2 to R and R3 to R. Yeah, okay. Let me give you an example of this. Can you recognize this? Yeah, so what is this? So this is usually we can say this is a sphere centered at the origin and whose radius equals to R, right? But we can also say, this is actually the level set of function. What function? A R square level set of function f is x squared plus y squared and z squared. Okay, so such a nice function can be actually modeled by the level set. Shall I give you another example? So x, y, z is x squared plus y squared minus z squared. Yeah, I just changed the sign. Can you imagine the graph of this picture, the level set, the one level set of this function? Can you visualize? Well, this is my idea. X squared plus y squared. Yeah, I will just change the. So once you choose the z coordinate, well, then this is going to be a circle centered at the origin and whose radius is square root of z squared plus 1, right? So, and choosing a z coordinate implies you're choosing a plane that is parallel to the x and y coordinate, x and y plane. So when you plug in z equals to 0, then that means the section of this graph, section of this surface at x and y plane should be the circle with center origin and radius 1, right? So when the intersection of this level set with x and y plane should be something like this. Now, shall I increase the z coordinate? So if I plug in z equals to 1, then that means, well, you're considering the intersection of this level set with the plane that is modeled by z equals to 1, right? So that is another plane which is parallel to x and y plane and whose z-intercept equals to 1, right? And in that case, the radius is slightly increased. So something more like this. And now, as you increase the z coordinate, then you're going to get something more like this. And as you decrease the z coordinate, then something like this. So therefore, if you combine all of them together, then you're going to have a graph that something looks like. Okay, it looks like a nuclear plant, right? Well, surprisingly, nuclear plant is, well, actually, some constant multiple. So the shape of the nuclear plant is, well, actually, some constant multiple of the graph of this guy. All right. Okay. All right. So this is how these two ways, drawing graph or drawing the level set, is two typical ways to visualize the real values functions. Okay. Now, okay, so much for the real values functions. Now I want to turn to the function from R to Rn. Okay. So this is not a real values function anymore. This is a vector values function. Okay. Okay. So I have so I would say the function is P. Suppose I have a function from R to Rn. And since the codomain of this function is in Rn, so therefore, it is very natural to assume that this function must have n component functions, right? N component. So in this case, P of t can be written as x1t, x2t, and x and t. Right? Do you remember the component functions? And yeah, these are all real value functions, right? Now, what is the best way to visualize or interpret this function? There are many different ways to interpret this, but the best way is we can interpret this guy as a curve. More precisely, we can interpret this guy as a parametrization of the curve. Hey, what does it mean by that? you should consider t as a time. So, and depending on time, as the time changes, then your position in Rn also changes. And if you keep track of all these, your positions, then you're gonna get a one-dimensional curve, right? How you travel in Rn so space as time t goes on, as time t varies. So this is the reason why we interpret this guy as a curve. Well, more precisely, curve is just some subset in Rn, one-dimensional subset. Curve is just in principle, curve is a one-dimensional. Sorry. Let me correct myself. Curve is, in principle, the subset in Rn, but parametrization is somehow different. Parametrization means the way you travel the given curve. So that means even though your curve is the same, but there are infinitely many different parameterization of the given curve. Why? Because suppose that I have this curve. Well, but you can travel in this direction, or you can travel in that direction, or you can travel like this, and you turn around and you go back and make the travel, make your trip. So this is the parameterization is the way you travel the curve. Therefore, even though your curve is the same thing, but parameterization may be different. And this is a parameterization, right? Because this gives you position for at time t, right? So this is, and what is curve then? Well, precisely speaking, the curve is the image of this function. 여러분, 그러니까 파라메트리제이션과 커브의 차이 아시겠죠? 그러니까 커브는 그러니까 그 선 자체, 곡선 자체를 의미하는 거고, 이거는 파라메트리제이션이죠. 그러니까 우리 시간 t에 따라서 우리가 어디 포지션을 여행하고 있는지에 대해서 그 정보를 가지고 있는 거죠. 그래서 똑같은 커브라 하더라도 파라메트리제이션은 다를 수가 있다. 이게 되게 중요한 아이디어예요. 그래요. 되게 중요해서 한국말 한번 강조했어요. 여러분, 저는 지난 시간에 제가 수업을 좀 일찍 끝냈잖아요. 저는 알고 있는 노로 바이러스 맨이었어요. 정말 죽다 살았는데 오피스에서 집에 못 가겠어 하고 바닥에 들어 누웠어요. 근데 이제 하여튼 겨우겨우 집에 갔는데 내가 이 얘기를 하는 이유는 뭐다? 여러분들은 아프면 빠질 수 있잖아요. 근데 저는 아파도 빠질 수가 없다. 그러니까 여러분들 꼭 오디오 하여튼 근데 이 자리에 와주셔서 감사하고요. 출석은 꼭 부르도록 하겠습니다. 6번 부르기로 했죠, 그렇죠? 그래요. 그래요. 그렇습니다. 그래요. 오케이. Okay. So let us try to imagine the curve given by this parameterization. Yeah. I have to be really careful. But okay. What is it? Can you imagine the curve? So this is R1 to R3. So this one must be a curve in 3 dimensions. Okay. So without the last component, then this parameterization is something we know very well, right? This is just a circle, revolving in counterclockwise direction. Okay, but well, we now have a non-trivial z coordinate. Therefore, instead of revolving just a single plane, but as time goes up, so the z coordinate increases. Therefore, this will make how many rotations? It is gonna make 2 rotations. Okay. And we have very nice name for such a curve. We say this is a helix or Nason curve. Mm. Well, this is another curve in 3 dimensions, 3-dimensional space. In this case, all these component functions, well, they are not linear, but they are a just degree 1 polynomial. And can you imagine this curve? So can you imagine can you imagine the image of this function given by this parameterization? All right, yeah. Well, not that obvious, but maybe I can try to represent, rephrase like this. 1, 2, and 0 plus t times 2, 3, and 4. Right? Aha. Now I have idea. So this one, this curve must be a straight line which is parallel to the vector 2, 3, and 4. But now that guy has been parallelly translated by 1 this much, 1, 2, and 0. Good. All right. Okay. What's next? The last kind of functions that we are trying to visualize is Rn to Rn. So, these kind of function have dimension of domain is the same as the dimension of the codomain. You can just say, oh, this is just a regular function from Rn to Rn. Yeah, that is completely fine. But, there is another way to visualize such a function. Sometimes not only mathematicians, but also physicists, they are trying to consider such a function as a vector field. So, have you ever heard about the idea of vector field? Well, in classical dynamics, the idea of vector field is widely used, just like the gravitational vector field or electromagnetic vector force field. They are all the vector field. What is the vector field? You have the space, and for every point in your space, so the vector is assigned at that point, right? And so, more precisely speaking, for every point in 3-dimensional space, a 3-dimensional vector is assigned at the point, right? So that is the vector field. So function from Rn to Rn, so means just suppose that you plugged in this point and you are able to get this vector. Then that vector is now assigned to this. Then we interpret that vector is now assigned to this point. By doing so, we can interpret this guy as a vector field. Yeah. So I tried to draw a silly cartoon of this. What about this? So this is clearly a function from R2 to R2. This is just simple. This is a very simple linear function, right? this function, linear function, yeah, you can say this is a linear function. That is great. Yeah, that is completely okay. But since the domain, the dimension of the domain and codomain, they're the same. So I try to reinterpret this guy as a vector field, just like this. So when the port, well, suppose that you plugged in 1, 0 to this function, then you're gonna get 0, 1, right? So that is why I have assigned this vector with this is clearly 0, 1. This is the reason that why I assigned this vector at this point. And what if you plug in 1, 1 towards your function? Then you're gonna get minus 1, 1, which is clearly this vector, right? Okay, so for every in this picture, I only assign, well, 2, 3, 4, 5, 6, 7, 8. Yeah, I only draw the 8 vectors, but well, actually there are infinitely many vectors on this, on this plane, and this is how you visualize such a function. Okay. This is a function from 3 dimensions to 3 dimensions, right? Because x is 3-dimensional vector, and the resulting vector is 3-dimensional vector multiplied by some constant. So this is from function from R3 to R3. So I want to visualize this. So if this point is the origin, and so if you plug in just a random point, then at this point, then the vector assigned at this point must be the vector which is parallel to the vector from the origin to this point. So well, so we call such a vector field a radial vector field. Radial vector field means that the vector field given by this function is pointing towards the outside. Yeah. So right, yeah, this one. So it should be something like this. So for each point on 3-dimensional plane, except for the origin, then you have but the unit vectors, the radial unit vectors with radial directions. Okay. Lastly, so we have this very important functions, vector field, which is fx is minus 1 over x times x. Oh, sorry. I forgot to add this cube. Well, I know since we have the negative sign here, the direction of this vector field must be opposite from direction of this vector field. But how also we have the third power in the denominator. So that means the length of this vector field is proportional to the inverse square from the distance from the origin, right? So I mean, so as you're getting far from the origin, then the length of the vector will decrease, rapidly decrease. such a vector field is assumed considered very important. So we say this is a inverse square field. And I try to draw the picture of that. Which should look like this. So this is all these vectors now, they are now pointing towards the origin. But as I getting far from the origin, the length of this vector is clearly decreasing, right? So this is a vector. Okay, good. Okay, so all right, and the last but not least. We have the composed function. So IF is a function from Rm to Rn, and G is a function from Rk to Rm. And if we compose these two functions in this order, then this composed function is going to be function from Rk to Rm and Rm to Rn. So therefore, this is a function from Rk to Rn and defined like this. But well, this is so obvious, so okay. I guess I'm okay to skip it. Now, I want to talk about the continuous functions. So multivariable function is about the multivariable calculus is about the functions in Rn to Rn. But well, if the behavioral function is completely random, then we may not be able to build any kind of reasonable theory from that. So therefore, we should expect all these our functions in our interest does not behave in completely random manner, but it behaves in some continuous manner. So that is why we are interested in the continuous function. Therefore, I should better say the multivariable calculus is a course about the multivariable continuous function. Okay, speaking of continuous functions, do you remember the epsilon and delta argument from your freshman calculus? Yeah, probably yes, probably no. But well, for those of you who do not remember, yeah. So we say a function from R to R is continuous at point A is defined by for every epsilon, you must be able to find some delta. So epsilon is the precision, tolerance, and delta is called the precision. For any positive epsilon, you can find a delta satisfying the following condition. Right. So you should regard this function, this definition like this. So suppose that this is the true value that you're looking for. But, well, we are human beings. We are prone to errors, so we can never be able to find the precise value. So this is our approximation. And it says this is tolerance. So, well, therefore, in order that our approximated function value is close to the true value by this error tolerance, then this is the precision. Then this definition tells us in order to attain this error tolerance, then our input value must be this much precise. So this is the definition of the continuous function. Okay, now it's time to introduce the definition of continuity in the multivariable calculus. It goes like this. I have function from Rn to Rm, and we say the function is continuous at this point if for every epsilon, I must be able to find a delta such that if x and y are this much close, then f of x and f of y must be, the difference between f of x and f of y must be less than epsilon. So this is our definition of continuous functions. What do you think? Yeah, I believe these two definitions are precisely the same. The only difference is we have these absolute values, but this time around we have these lengths of vectors. These are only difference. This is the only difference, and the remaining thing, they are all the same thing. They all carries over. Okay. So if you're good about the continuous function in freshman calculus, then you're good. Okay. But being able to tell if any given function is continuous or not is slightly complicated. Just like this. Okay. Let me try to prove that this function, this is very easy function. This is just a degree 2 polynomial. Well, so it looks like this function must be continuous at every point. But well, anyway, let me try to show that this function is continuous at the origin. How? By using this epsilon and delta argument, our long-lost friend. All right, so before I give you the proof, so let me try to analyze under what condition f of x and f of 0 is less than delta epsilon. So, well, this is the domain of this function is R1. So in this case, yeah, I can still use these absolute values instead of the length. So fx comma y minus f0 and 0. This is just x squared plus y squared, right? And I am looking for the condition, under what condition this guy is less than epsilon. This guy is less than epsilon. Sorry. This one is just x comma y minus 0 comma 0 and square. So in order to attain this inequality, in order this guy to be less than epsilon, and our delta should be less than, so this is the delta squared, right? This is less than delta squared. So therefore, our delta squared must be less than epsilon. In other words, our delta must be less than square root of epsilon. Right? All right, so I will prove this. For any epsilon, we choose our delta to be square root of that number. Then if the distance between x comma y and 0 is less than delta, then this is what? This is same as x squared plus y squared is less than epsilon. Then f of x comma y minus f of 0, which is x squared plus y squared. And oh, sorry. Yeah, I'm confused. It's less than epsilon. Okay. Okay. All right. Okay. So well, in principle, so every time when you're dealing with any function, then first thing that we have to do is we will need to make sure the function is continuous. But well, proving the continuity of the function, each time you encounter function, it looks like very inconvenient. So we have a couple of nice theorems. The first one is every linear function is continuous. Everywhere. So linear function has very nice property. I have a linear function from Rn to Rm. This is a linear function. Then, well, there is an m by n matrix C such that L of x is represented by C times x. Well, there is always such a matrix because every linear function can be represented by the matrix. The existence of such a matrix is guaranteed. Now, for any epsilon, we choose our delta to be 1 over C times epsilon. Hey, what is this? This is nothing but the matrix norm of this guy. Do you remember? Matrix norm? Yeah. So, if x and y is less than delta, then L of x minus L of y. But since my function is linear, so I can say Lx minus y. But this is C x minus y. Now, because of the inequality that we proved in the beginning of this class, this is bounded by C times x minus y. And since this guy is less than delta, and delta is this one, so this is less than C times 1 over C times epsilon, which is epsilon. Right? So for any epsilon, we could find a delta so that satisfy this blah, blah, blah condition. Okay? Okay, good. All right. So we were able to prove that the linear functions are always continuous. And we now can, so now I am about to introduce many interesting, but many useful, but many obvious theorems without proof. So therefore, from now on, you can take advantage of all these theorems without any justification. Good, good. The first one is the definition. Yeah, this one is definition. We say a function is continuous, not just a single point, but continuous on entire domain if f is continuous at every point in the domain. So this is definition. So this is the definition of continuous on the entire domain. Okay. All right. So this is obvious. And the next definition is convergence of a sequence. Well, in freshman calculus, you know the sequence of numbers. But this is the multivariable calculus course, so we have not a sequence of numbers, but sequence of vectors. So the x1, x2, xk, they are all vectors. And the sequence of vectors is said to be converging to a point x if for every epsilon, you can find an integer n so that if the index of this term is greater than this guy, then xk minus x is less than epsilon. So this is another, this definition is also very similar to the convergence of the sequence in the freshman calculus, right? Okay, yeah. So this is the definition of convergence of the sequence. Convergence of the vector sequence. And well, there is a theorem. I have a continuous function f, and on the domain of this function, we have a sequence of vectors. So these vectors from x1 to xk, all these vectors, they are the vectors in this guy, in this set. And it is assumed that these vectors, sequence of vectors, are converging to a point x in D. Then what? Then the claim of the theorem is this newly obtained sequence. This is another sequence of vectors, but these vectors, this sequence is obtained by composing the function with the sequence. So these vectors are vectors in, not here, but there. So they are m-dimensional sequence of vectors, right? Okay. And then these guys are converging to f of x. Okay. And from my viewpoint, this is very obvious. So I don't think I will need to give you the proof of this. Well, even though this doesn't seem to be very clear to you, but well, okay, just let me just take this for granted. So I will pass. And another obvious theorem is I have a function Rn to Rm. Then because the codomain of this function is Rm, so it must have m many component functions from f1 to fm. And each of these component functions, they are function from Rn to R, right? They are all real valued functions. So we have these functions, we have these m many component functions, and this theorem says the function is continuous if and only if if each component function is continuous only. So continuous of the vector value function is the same as continuity of the component function. All these component functions. Okay. And for me, again, this sounds very obvious. Yeah, so I will also skip this. But so therefore, from now on, we don't need to spend time to prove why this function is continuous. Remember, this was helix, right? And I am pretty sure that this function is continuous. Why? The component functions, which is sine and trig functions and polynomial, they are continuous. Therefore, the resulting function x must be also continuous. Okay. Good. So these will save us too much time. This will save us time. Continuous. And another easy theorem about if you have we have two real values functions, f and g. So our convention is when we are referring to functions, and if they use the lowercase symbols, then that usually refers to the real values functions. So we have two real values functions, and they are having the same domains. Then in such cases, we can define the new functions such as f plus g, f times g when 1 over g. And under reasonable assumptions, then they are all continuous. So, well, I can also skip the proof of this. And finally, if you have two continuous functions, and if you can compose them, then the composed function is also continuous. Okay. This is also very obvious. Okay. So just one more thing to add. Because of this last theorem, theorem 2.7, this theorem, the last theorem, can be used especially when you try to prove some function is not continuous. Just like this. Suppose that you have functions. Suppose that you have a function and that is continuous at this point. Then for any curve continuous, I should say path. Here, this A0 should be considered a just random point in the curve, a random point in this interval. So this is a curve from this interval to Rn, and this is a function from Rn to Rk. And then, since this composed function x to f of x must be also continuous at this point, right? Because of the theorem. So as t is tending to a0, then this value must be f of p. Yeah, this statement seems to look very obvious, but this easy observation sometimes helps us to tell if any given function is not continuous. Just like this. I have a function x squared minus y squared over x squared plus y squared. If x comma y is non-zero, and suppose that I have such a function. So this is a function from R2 to R, real values function. And other than the origin, I am pretty sure that this function must be continuous, right? Because this is just polynomial over polynomial, right? So because of this theorem, so well we know this function is continuous for all x's other than the origin. But the question is this guy continuous at the origin? Well, then if this guy were continuous at the origin, then for any path from R1 to R2 such that xt equals 0 equals the origin, then this limit must be well defined and equals to this one, 0. But that means if you can find at least one path such that whose limit is different from f of p, then that is going to be the evidence that your function is non-continuous at the origin, right? Okay, so I'm going to show you by looking at the example. So this is the plane. This is the domain of function small f. And then this is the point in question, right? The origin. And we will take two different paths. The first one is this one. We let xt is t comma 0. Then if we compose the function with this path t, and as t goes to 0, then this is what? This is t goes to 0, and this is x coordinate is t and y coordinate equals to 0. Therefore, if you plug in these two guys here, then you have t squared minus 0 squared over t squared plus 0 squared. So which is just 1. Right? And this is what? This is a clear violation that, and if this function were continuous, then this limit must be 0. But this number is clearly different from 0, right? So therefore, we are safe to say this function is non-continuous at the origin, right? Okay. The next definition is the curve. Oh, yeah. We already discussed the curve. So suppose that you have a function from R1 to Rn, then curve is not of this function itself. This function is called parametrization. I told you this is the parametrization has the information of how you travel the given curve. So curve and parametrization, yeah, even though these two words are, yeah, often many times they are abused and interchanged and considered interchangeable, but in our course they are different, right? And curve is it clearly says the range of the function. Right? 그러니까 함수의 이미지가 커브고 커브예요. 함수 자체는 parameterization. Okay? And well, xa and xb. So if the domain of function is a closed interval, and endpoint of these two intervals are a and b, and if xa and xb, we say these 2 points are the endpoint of the curve, right? And if those two endpoints agree, then we say this is a closed curve or a loop. Okay? Closed and loop. We say a subset is connected. What do I mean by a set is connected? If for every pair of point P and Q in A, there is curve in A with endpoint P and Q. So this is a picture. Yeah, I'm going to show you an example and non-example of connectedness. This is R3. Just consider this solid with interior. And this is clearly connected because for any two pair of points in this set, this is set A, say this is P and this is Q. Just choose any 2 points in this set A, but no matter which 2 points you have chosen, but you can still find a curve whose end that lies in A and endpoint is P and Q. Well, for instance, like this. You can always find at least one such curve. So this is connected. But however, this is not. Well, A is the union of this piece and that piece. Well, taking the union of this, the whole thing we're gonna call the A. And I am pretty sure that this is not connected. Why? Because, well, in order to be connected, then for any pair of points, you should be able to find a curve in A whose endpoints are these 2 points. But in this case, if your one point is here and another point lies there, in that case, you can never be able to find a curve whose endpoint is those 2 one, and that lies in this set A, right? So this, because of the reason, so this guy is not connected. Okay. Yeah. I just ran out of time. Yeah. All right. Okay. Let me say this is for today and see you next time.